Hello, I'm Seema and welcome to part 13 of the chapter Chemical Bonding and Molecular Structure. The earlier attempts at explaining chemical bonding were done by Lewis, and Lewis took electrons as electron pairs around the core of an atom, and he tried to explain how in chemical bonding the octet is completed around the central atom and how the bonding takes place. He could not explain the structures of molecules. It was just based on the electronic configuration, or rather the valence shell. The Vesper theory also talked only of the valence shell, and it differentiated between these electrons as lone pairs and bond pairs. And this theory tried to explain the structure based on the repulsion between the pairs of electrons, and that was how it explained the symmetrical structures. And the a little distorted structures were explained on the basis of difference between the lone pair repulsion and bond pair repulsion. But both these theories did not talk of the S and P or D. They did not take the orbitals, talk about the orbitals. And how could you explain the structures of molecules and chemical bonding on the basis of these orbitals? This was done by the next two theories, which were called the valence bond theory and the molecular orbital theory. We are now going to study about the valence bond theory. The valence bond theory was given in 1927 by two scientists, Hitler and London, and it was further modified by Pauling and a few other scientists. That is just about the history of how it came into being. What is this valence bond theory? We commonly abbreviate it as VBT also. So the valence bond theory, or the VBT, it was based on 5 main points that it focused on. What did it talk about? It explained chemical bonding and molecular structure on the basis of atomic orbitals. Now this was the first theory which talked about the atomic orbitals. Next, it saw the electronic configuration and explained chemical bonding on the basis of electronic configuration. And there were 4 points. The atomic orbitals, electronic configuration, the third point and the fourth point were the idea of orbital overlap and hybridization. Now these two points of focus explained the structure of a molecule. The first two, that is atomic orbitals and electronic configuration, they told us about the basic chemical bonding, and the orbitals and their overlap, and then hybridization. These were the 2 points that could explain the structures of molecules. Now, if you imagine that you have 2 atoms and they have to form a bond, I would like you to think of yourself and your friendship with someone who is new. A new person has come into your class, and you are thinking of making that person a friend, or you are new in a class and you have to choose who would you make your friend. Now there is someone that you really repel a lot. You somehow don't like that person. Nothing about the person you like, the way he talks, the way he walks, the way he treats other people. You're just observing different people and you realize that this is one person I really don't like. So you are kind of repelled by that person. So would you ever care to make friends with him? No. But then there is this other person who you find has certain good qualities, and you are attracted to that person, and you also find that there are certain, bad qualities about him also. And then you start weighing. And when you weigh, you want to see whether the goods, the ones that you're attracted to are more, or the ones that you are repelled by are more. You will ultimately make friends with that person whose good qualities or attractions outweigh the repulsions. Isn't it right? You would always try to make friends with a person who you are attracted to, whose qualities you find appealing, and every person has good and bad qualities and what is good for me may not be good for you. So according to your perspective, if these are the things that you like in a person and these are the things that you dislike, if the things that you dislike are lesser, you may make friends with that person. But if the things that you dislike are more, you will not go ahead and try to be very enthusiastic about that friendship. Chemical bonding is a kind of a bond, it's a friendship. So atoms which have to form a chemical bond, they have two types of forces when they come closer and they are approaching each other to form a bond. What are these forces that they would experience? They would also experience forces of attraction and forces of repulsion. And why do these forces exist? Because atoms have positively charged nuclei and negatively charged electrons. And when you have opposite charges, then we know that opposite charges attract each other and similar charges repel each other. So you will find forces of attraction and forces of repulsion that come into play when two atoms are approaching, they're trying to come closer to make friends with each other, that is to form a bond. So what are the forces of attraction? Let us assume that we have two hydrogen atoms and they are approaching. Why do we take hydrogen? Because they have only one electron and one proton. So we're trying to keep it very simple to understand these forces of attraction. There are two atoms of hydrogen and they are approaching each other. And what are the forces of attraction that you feel exist in this system? Two atoms approaching each other with the intention of forming a bond. Let us say now Na and Nb are the nuclei of hydrogen A and hydrogen B. And Ea and Eb are the electrons of hydrogen A and hydrogen B. We find that the nucleus of hydrogen A attracts the electrons of hydrogen A, right? These are the forces of attraction which are pre-existent. Then the nucleus of hydrogen B attracts the electrons of hydrogen B, understandable. Now, as they come closer, the nucleus of A starts attracting the electron of atom hydrogen B. Similarly, at the same time, the nucleus of B starts attracting the electrons of hydrogen A. So, these are the four forces of attraction that come into play when two hydrogen atoms are approaching each other. What are the forces of repulsion? When the two hydrogens were separate, whatever their forces of repulsion were, first of all, we took hydrogen because we did not want the interprotonic repulsions and interelectronic repulsions. We just wanted to take a very simple example here. So we will assume that both the hydrogens have one proton, one electron, and there was only attraction in play. And when they come close, now what are the repulsions that will come into play? The nucleus of hydrogen A will start repelling the nucleus of hydrogen B. And because both of them are positively charged. And the electron of A would repel the electron of B. So we have two forces of repulsion here. Now, the number of forces does not tell us about the magnitude of the forces. When will a friendship take place? Not when the number of things, when the magnitude also is important. How much is the attraction and how much is the repulsion? There may be 4 types of attractions and 2 types of repulsions, but when the attraction, the magnitude of the attraction is greater than the magnitude of repulsion, only then the bonding takes place. Right? Now this is the first thing that you have to understand, that forces, it should be energetically feasible. Any reaction only takes place if it leads to stability. That is, if the molecule that it forms is lower in energy than the individual atoms. Stability in chemistry means a state of lower energy. So when the forces of attraction are greater than the forces of repulsion, that is when bonding takes place. Now, there was one more thing about the Lewis approach and the Valence and the Vesper theory. They did not talk of bond lengths. They could not tell about the bond length and the bond enthalpy. They had no idea about this. But Valence bond theory, when it talked of this idea of forces of attraction and forces of repulsion, it was taking energy into consideration. Now imagine these are 2 atoms which are far apart, and this is the distance from the nucleus. We find when they are quite far away, there are the forces of attraction or repulsion, we find on the whole it is 0. As they come closer, the forces, now they are coming closer and the forces, other forces of repulsion and attraction are coming into play. As At 74 picometers, when there is an overlap of the two atomic orbitals, the 1s orbitals, that is when we find that at 74 picometers, the forces of attraction are the highest and the forces of repulsion are the least. If we bring the two atoms still closer together, you know the atom is mostly empty space. It is possible to crush them further together. So if you bring them closer than 74 picometers, the forces of repulsion become so much higher that the system becomes unstable. So at 74 pico, and even anywhere beyond 74, if you go above 74, the forces of attraction are not strong enough. So we find at 74 picometers in a molecule of hydrogen is that ideal distance at which the energy of the energy of the molecule is the least and the forces of attraction outweigh the forces of repulsion. And valence bond theory says that this is what is called the bond length. It is this distance at which the molecule would be formed, and this would be the bond length. And since the energy here is the least, the amount of energy which will be required to break that bond of 1 mole of that substance would be the enthalpy of dissociation. So in the case of a hydrogen molecule, the bond distance or bond length is 74 picometers and the enthalpy of atomization or the enthalpy to break it would be 435.8 kilojoules for 1 mole of hydrogen. Right? So now you have understood how energetically the chemical bonding should be feasible. The next point is the idea of the electronic configurations. Of course, it was done in the electronic configurations. We have done that whatever is the number of electrons, the orbitals which are half filled, they are the ones that form bonds. Okay, I'll just come to that a little later when I start explaining these examples. The next concept was the concept of orbital overlap. When orbitals overlap, that is when a bond is formed. When two atoms come close to each other, these orbitals, and they touch each other, some of the outermost shell just merges into the neighbor. The orbital that has to share the pair of electrons, those two orbitals, they merge to some extent with each other. And this area of merging is known as the area of overlap. And it is said that the orbitals overlap. The overlap is actually a merger. Both of them, they just merge. For some distance, they penetrate into each other. The orbital is only a space. So that space, they merge, and this merger is known as the overlap. Overlap also can be positive or it can be negative. Positive overlap is feasible overlap. That is when a bond will be formed. And if there is a negative overlap, that is a non-feasible overlap, the bonding will not take place. For overlap to take place also, the overlap should be feasible. Only then the chemical bond is formed. And sometimes you may have positive overlap, you may have negative overlap. Positive leads to bonding, negative does not lead to bonding, and there is a third possibility, that is of zero overlap. Zero overlap is the overlap itself is not possible due to the shapes of the orbitals. So let us now study about these overlaps. We know that where s orbitals are spherical in shape, and when they overlap, they can simply overlap in any direction. But if both, you also have to remember that when the two electrons that are present and this overlap is taking place, they should be in opposite spins. They should be in opposite spins, only then the overlap would be positive. But since s orbitals are not directional in nature, we now come to p orbitals which are directional in nature. First of all, there are two types of overlaps that are possible. The head-on overlap and the sideways overlap, right? The head-on is where the overlap is from the head to head. The overlap would be most effective. The more the overlap is, the more is the area of overlap, or the more is the merger of the outermost orbitals, the stronger would be the bond. The area of overlap decides how strong the bond would be, because that is the greater merger. The more the merger, the stronger will be the bond. So what are the type of mergers that can happen? We know that s orbitals are spherical, so it will be a head-on overlap. That kind of an overlap is known as a sigma overlap, when the overlap is taking place head over head. And since it is spherical, the s orbital, you will not even come to know what head over head is, because there are only two heads and you are merging the two heads. So when you come to p orbitals, we know p orbitals are aligned along the three axes: the x-axis, the y-axis, and the z-axis. And we always, in chemistry, just for the, as convention, we take the z-axis to be the internuclear axis, right? It's just, you could have taken any, but just to make it easier and to assume that every time it is z, 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 which is coming in, touching each other head on. And if there is pi bonding after that, that would be the y or the x orbitals. I'll just come to those now. P, Z and PZ, when they overlap, when they come head on, they overlap to form a sigma bond. So these are two p orbitals, they are two dumbbells, they are along the z-axis, that is the z-axis is this way, and because I said the head on is always the z-axis, internuclear axis is z-axis. So when they come, and these two, they come and hit, do you see the heads are hitting each other, and when they come and hit, and they merge, if the overlap is effective, if this merger is such that both the lobes, you assume one is positive and the other is negative. The overlap is effective when you have the same sign. These are not electrical charges. This is just to show you the similarity. The positive lobes, when they come one over the other, they will reinforce each other. But if you have positive and negative, it will cancel out each other. It is not electrical charges which are being attracted. These lobes are just positive and negative to show perhaps the opposite spins of electrons or something. But this is when positive falls over positive, a reinforcement takes place. So the positive lobe falling over the positive lobe would lead to reinforcement, and such an overlap is effective and the bonding will take place. And since it is head-on, since it is a head-on overlap, it would be a sigma bond that will be formed. Now, here we see PZ and PZ, both of them came close, and when the overlap took place, both the lobes that overlap are positive. So this is a positive overlap. It is effective overlap. On the other hand, if positive fell over negative, let us say that on this side it is positive and positive. It is effective overlap, but if one was positive and the other was negative, the overlap would not be effective and the bonding will not take place, and the overlap is known as a negative overlap. If you have PZ and S orbital is spherical, so PZ and S, when they overlap, the overlap will be positive if again S and PZ, that lobe should go and merge with the s orbital, which has the same sign. Although these are not electrical signs, but they should have the same sign. Then you have PZ and S. When you again have the negative lobe falling over a positive s orbital, the overlap would be ineffective. But in both these examples, or rather 4 of these examples, these two actually do not exist, because if this overlap occurs, the bonding will not take place. So these two would lead to the formation of sigma bonding. Sigma bond is the first bond which is formed between two atoms, which is formed by the head-on overlap of the orbitals that are sharing their electrons. Then you have pi orbitals, pi bonds. Pi bonds are the bonds which are formed after the first bond is formed. If there still is deficiency of electrons, more orbitals try to overlap. Now, if the electrons are present in the p orbitals, the pz was head-on, but px and py are perpendicular to the pz axis. So if they are perpendicular to this orbital, if the pz was like this, let us say p Y is here, Py and Py, if they have to overlap, they will overlap sideways now. Such a sideways overlap is known as a pi overlap, and pi bonds are formed as second or third bonds, right? So the first bond, if there were three p orbitals which were forming bonds, the first one would be sigma, the second would be pi with py, and the px axis also would overlap, and that would form the third bond. So that is how the pi bonding takes place. Again, when the pi bonding is taking place, if the positive and positive lobes fall together, it is effective and you have a positive overlap. But if you have positive falling over negative and the overlap is not of the matching lobes, the bonding does not take place. So this is negative overlap. So this was px orbitals overlapping, and then py orbitals overlapping in the diagram in 2 dimensions. I just tilted this to show you that these are not in the same direction. This was the internuclear axis, the x-axis I've shown like this, and the y-axis, you can imagine these two lobes going behind the board and these two lobes coming in front of the board. The next type of overlap is the zero overlap. Zero overlap is where you have p orbital, and the p orbital is here, and the two lobes are here, and you have the s orbital coming and overlapping. If the s comes and overlaps like this, the lobes are overlapping. But if the s orbital comes and tries to merge here in the center, it does not overlap with any of the lobes. It's only coming to the nucleus, towards the nucleus, and the two lobes are in another direction. So this kind of a node, there is no overlap at all. Overlap is not possible. So such an overlap is known as a zero overlap. It is absolutely ineffective. There is no overlap at all. On the other hand, if you have the p orbital, the px, let us say, of one atom trying to overlap with the py of the other orbital, of the other atom, px and py will have the same problem. They are perpendicular to each other. The lobes should overlap, and if the lobes are not overlapping, it's just coming close to the axis and there is the center, the nucleus, the overlap is not effective, and again such an overlap is known as a zero overlap. So this was about the orbital overlap. And remember, the greater the area of overlap, the stronger will be the bond. So the overlap gives us an idea about what the structure of an atom will be, because we know that the p orbitals and the d orbitals, they are directional in nature, while s orbitals are spherical. So using this knowledge, the valence bond theory tries to explain the structures of molecules. Now these bonds, they have directional properties. When we say directional properties, it means the bonds should have specific directions. They should have fixed directions, or the molecule has fixed shapes. And this was known to us. According to spectroscopic studies, we knew that molecules have specific shapes. Methane has a structure which is tetrahedral, and every angle, it's a symmetrical structure, and every angle is 109.5 degrees. Ammonia has a 107-degree angle, and the structure is pyramidal. Water has a 104-degree bond angle, and it is a bent structure. Now this, how do you explain this on the basis of valence bond theory? We would try to explain it on the basis of our knowledge of this overlap first, and then see what was deficient. Why did we have to bring in the next concept, that was hybridization? But before I come to that, let us try to solve the structures of these, explain the structures of these molecules without using hybridization. We are using the earlier concepts, that is electronic configuration, the atomic orbitals. We'll take those into consideration. Now carbon is the sixth element, right? What is the configuration of carbon? The configuration of carbon is 1s2, 2s2, 2p, 2p. If I try to make the orbitals like this, this is 1s2, this is 2s2, and that is 2p. 1s, 2s, and 2p, three orbitals of 2p. If I fill it up now with electrons, carbon in the ground state has 2 electrons in 1s, 2 electrons in 2s, and two electrons singly occupying the 2p orbitals, px, py and pz. Right? Now, carbon, in order to complete its octet, requires four electrons, because it has 4 electrons in its outermost shell, and it needs 4 electrons to complete its octet. Now, according to the valence bond theory, the half-filled orbitals, they overlap with each other, and then the bonding takes place. Right? One electron from one orbital of one atom, 1 electron from that orbital of the other atom, then there is an overlap and they share this pair of electrons, and this pair of electrons belongs to both of them, and they try to acquire their octet by forming these bonds. When carbon is supposed to react, now in this state, it has only 2 orbitals which can form bonds, but it needs 4 electrons. So just before carbon has to react, one of its electrons from the 2s orbital, it jumps up to the 2p orbital. So one of these electrons jumps up here, and of course it requires some energy to do this, but when it does this and it forms the bonds, the amount of energy given out would be so high that this amount of energy that it used, a little inconvenience in the beginning, it's just that, because in the end, when it forms 4 bonds and the octet is complete, the amount of energy that would be given out and the amount of stability it is going to require is going to be much more. So this electron, it jumps up to the 2p orbital. Now we have 4 unpaired electrons in 4 orbitals. And according to valence bond theory, these 4 orbitals, hydrogen has only the S1s1 is hydrogen. Right? Now, 4 hydrogen atoms which have these 1s, they come and they overlap with these 2s, 2p orbitals, and the 4 bonds are formed, and these 4 bonds, how should the direction be? According to our understanding of this, that is the overlap, what would we expect? We would expect that carbon has 2 types of orbitals which are participating in bonding. One is the 2s orbital, and there are 3 2p orbitals. And hydrogen, of course, all of them have s orbitals, so it is not hydrogen which is going to affect the structure. The structure of methane is very, very symmetrical. But according to this, we find that the s orbital should combine in any direction to any hydrogen to form one bond, and these 3 should form bonds at 90 degrees to each other. Do you see? The hydrogen and the Z should form the internuclear axis. Another hydrogen is forming a bond along the y-axis, and another hydrogen is forming the bond along the x-axis. So there should be 3 bonds which are perpendicular to each other, and there should be 1 bond which should have no direction. But we find that methane has a structure which is very, very symmetrical. It has a tetrahedral structure, and every bond is the same. That is 109 degrees and 28 minutes or 109.5 degrees. So this is something that could not be explained on the basis of our knowledge of just the overlap of orbitals and that they have directional. Yes, they have directional nature, but directional nature cannot be explained only on the basis of this knowledge. If you take ammonia also, nitrogen is the 7th element. So what would nitrogen have? Nitrogen would have 2 electrons here. Right? So, sorry. Carbon, nitrogen. So, nitrogen would be 2s2, 1, 2, 3, 4, 5, 6, 7. So it has these 3 p orbitals. Now it is nitrogen, yes, and it is 2p3. So it has 3 p orbitals, and these orbitals have to overlap with the 3 hydrogens to form the bonds. So you would expect, according to this knowledge, you would expect the angles of ammonia to be how much? 90 degrees again, because px, py, pz, they are perpendicular to each other. And we find that in the structure of ammonia, the angle is not 90 degrees, it is 107 degrees. It's a pyramidal structure. And the Vesper theory explained that it has a lone pair of electrons and the lone pair bond pair repulsion is higher. It should have been a symmetrical structure, should have been tetrahedral, but it pushes it down. It did try to explain that, and to some extent you are convinced by it. But this problem here in valence bond theory was explained on the basis of another concept, which was known as hybridization. And hybridization is which finally explained the structures of molecules or these distortions. And what is hybridization? That when electrons jump up to higher orbitals just before reacting, and in the excited state they jump up and they make orbitals available for bonding, they also undergo a transformation, a change in their energy, or a redistribution of energy between themselves, and they form identical orbitals. And these identical orbitals, that is, if carbon, there was one electron which jumped up here in the case of carbon, and there were 4 of these orbitals, all the 4 orbitals would again merge and re-emerge in the form of 4 identical orbitals. This was known as they get hybridized. This was known as hybridization, that they get hybridized and these 4 orbitals would be identical, and therefore you could explain this structure on the basis of that hybridization. That is, they merge and they emerge again in the form of identical orbitals. So in the next video, I'll be explaining hybridization to you. If you found this video useful, please give it a thumbs up and subscribe to my channel, recommend it to all your friends and help me to spread word about them, and please keep returning for more videos in chemistry. Thank you for watching, and bye bye for now.